Hi, I'm Miss Hearn. If you like this video, please give it a thumbs up. That will help other students to find the video. You can also subscribe to my channel, Miss Hearn Mathematics, for more math videos. Now we have a sandwich theorem for sequences as well, which basically tells us that if there's a sequence that's squeezed between two sequences, and if the smallest and the largest of those converge, then so must to a particular value, then the one in the middle must also. So, for example, you can show that the cosine of n over n converges to 0 by just remembering that the cosine of n has to be somewhere between 1 and -1. So that means that cosine of n over n has to be between -1 over n and 1 over n. And we know that the limit as n goes to infinity of 1 over n is 0. And we also know that the limit as n goes to infinity of -1 over n is 0. So that together, that implies that what's in between them must also go to 0. Okay, so that's one example of using the sandwich theorem. Here's another one. We can show that 1 over 2 to the n must go to 0 because the sequence that's all zeros will always be less than or equal to 1 over 2 to the n. And the sequence 1 over n is always bigger than 1 over 2 to the n. Now, when I first looked at that, I had to write out what are the values of n and what are the values of 2 to the n to kind of convince myself that 1 over 2 to the n, in fact, is always less than or equal to 1 over n. So let's do that real quick off to the side here. So if n is 1, then 1 over 2 to the n, let me make myself a little more room. So if this is n and this is 1 over 2 to the n, when n is 1, we get 1/2. When n is 2, we get 1/4. When n is 3, we get 1/8, and so on. So you can see that 1 over 2 to the n really is always less than 1 over n. Now then, since the limit as n goes to infinity of zeros is 0, and the limit as n goes to infinity of 1 over n is 0, then this guy has to go to 0 as well by the sandwich theorem. Okay, and another example of using the sandwich theorem would be when you have, do you remember what this is called from the first part of the lecture that you guys watched on the video? When you have -1 to the n power, what happens when you have that? What happens, what characteristic do the terms of the sequence have when you have -1 raised to the n? Very good, Sierra. That's called an alternating sequence. That's right. So when n is 1, you're going to get a negative. When n is 2, you're going to get a positive. When n is 3, you're going to get a negative, and so on. Okay. So what we have here is an alternating version of the 1 over n sequence. So that means it's going to be greater than or equal to the -1 over n. Sometimes it's equal to -1 over n when we have an odd term, and sometimes it's equal to 1 over n when we have an even term, but it's always in between the two. It's never going to be less than the negative version. It's never going to be greater than the positive version. But as we saw right here, we know that each of those is going to go towards 0. So that means that the alternating sequence must also go towards 0. And then finally, another example, it's sort of related to what we just saw there. If the absolute value of a sequence, of each term of a sequence, is considered a sequence itself, and we know that that absolute value of that sequence goes to 0, then that means the original sequence also goes to 0. And the reason is because the sequence without the absolute value is always either going to be the positive or negative version of the absolute value sequence, right? It's either going to be equal to that sequence or it's going to be its opposite. So another way of saying that is written right here. A sub n either is the negative version or the positive version. It never goes outside of those two bounds. It's in between. And if we know the absolute value is going to 0, then that means the opposite of the absolute value is also going to 0. And then that means that a sub n in between is also going to 0. This is actually something that comes up later on too, when you, sometimes it's easier to work with the absolute value of a sequence rather than the sequence itself if it changes signs. So you work with its absolute value and determine if it converges, and if it does, then you know the overall sequence converges too. So this can be useful. Okay. There are certain sequences that come up a lot, and we can use them to help us with other sequences and problems. So there are 6 formulas right here that you should be familiar with. First of all, we proved that the natural log of n over n converges to 0 just a few minutes ago. So that's one of them. That's number 1. Natural log of n over n converges to 0. And then another one is the nth root of n converges to 1. The limit as n goes to infinity of x to the 1 over n converges to 1 as long as x is some positive value. This is a fixed value. This is not varying. Usually we would use like an a or something, but for whatever reason the author decided to use x's. And then, and that's the same with number 3, 4, 5, and 6. The x is a fixed value. Okay, the limit as n goes to infinity of x to the n is always going to be 0 if the absolute value of x is less than 1. In other words, it's a fraction. And then the limit, where do you recognize this limit from somewhere in college algebra? This one is related to the application where you found continuously compounded interest. The limit as n goes to infinity of 1 plus x over n to the n power is equal to e to the x. It's usually the first place you see the definition of e to the x. And then this one, the limit as n goes to infinity of x to the n over n factorial is equal to 0. So a lot of times people are not familiar with this factorial notation. That's the exclamation mark. So I've written off to the side the first few factorials. Factorials get their name because they are products, right? So we have a bunch of factors, things being multiplied. And let's start at the bottom here. 5 factorial is the product of all the positive integers up to 5. So 1 times 2 times 3 times 4 times 5, which is 120. 4 factorial is the product of all the positive integers up to 4. So 1 times 2 times 3 times 4 is 24, and so on. 3 factorial is 1 times 2 times 3, which is 6. 2 factorial is 1 times 2, which is 2. 1 factorial is just 1. And here's a weird one. 0 factorial turns out to be 1 as well. It has to be for other operations to work out. So that's by definition. So that's what they're referring to in this limit here. You have maybe the limit as n goes to infinity of 5 to the n over n factorial. That's going to be equal to 0 because it says for any x. So I chose x to be 5 in this case, any fixed value. All right, so let's use these facts to find the limits. They're giving us the nth term of the sequence, and they're asking us to determine the limit of the sequence. So we have natural log of n squared over n, and we want to figure out the limit of the sequence. So which of the 6 rules does that appear to be related to? Part A there, which of the 6 rules does it look related to? Yeah, it looks like it's related to number 1, right? So can we rewrite this somehow using algebra so that it is even more obvious how it relates to number 1? Because in number 1, what's the difference? In number 1, it's the natural log of n. And here we have the natural log of n squared. But what can we do with that power? So see, we'd like to have natural log of n, but we have natural log of n squared. Very good. We can bring it out front. Very good. All right, so if we do that, we're going to have 2 times the natural log of n over n. What's that going to converge to? Very good. It's going to converge to 0 because this is the same as 2 times whatever natural log of n over n converges to. So that's 2 times 0, which is 0. Okay, now let's look at part B. Maybe I need to zoom in a bit there. Okay, so for part B, we have the nth root of n squared. All right, so we've rewritten it as n to the 2 over n, which can be rewritten as n to the 1 over n squared. And so which rule does this one appear to relate to? Rule number 3. Okay, rule number 3. No, take that back. It's not rule number 3. I can see why you think so, but it's actually not. Do you know why it's rule number 2 instead of rule number 3? So rule number 3 would apply if we had something like the limit as n goes to infinity of 5 to the 1 over n. So when you have a fixed value, that's what that x is. Whereas rule number 2 is actually n to the 1 over n. So both the power and the base are changing. They're varying. All right, so then we're going to have n to the 1 over n. The limit as n goes to infinity is going to be 1, and 1 squared is going to be 1. You with me? This was rule 2, not rule 3. And this one was rule 1. Okay, how about part C? What could we do with that one? This one's actually going to relate to more than one rule. Which 2 rules can we apply to this, or can we use to help us figure this one out? We're going to use 2 rules here. We're going to rewrite it so we can apply 2 different rules. Nth root of 3n. Yes, 2 and 3, because we can break this apart into the nth root of 3 times the nth root of n, or 3 to the 1 over n times n to the 1 over n. So then the 3 to the 1 over n is approaching 1. That's rule 3. And the n to the 1 over n is approaching 1. That's rule 2. So we get 1 times 1 is 1. How about part D? We want to know what negative 1/2 to the n power is converging to. Which rule or rules could we use? The absolute value of negative 1/2 is less than 1. It's 1/2. So that means that rule 4 applies. And according to rule 4, if you have a value whose absolute value is less than 1, and you raise it to the nth power, that limit is going to be 0. So this approaches 0 because the absolute value of negative 1/2 is less than 1, and rule 4. Okay, now let's look at part E. N minus 2 over n to the nth power. Okay, which rule or rules could we use for this one? Yes, how can we see that rule 5 applies there, Jason? You're correct. But we have to rewrite it a little bit to see that, right? Or anybody else who wants to answer that. How do we rewrite it so that we know that? Good. So you're going to divide each term by n. So we have 1 plus negative 2 over n to the n power. And it says that for any x, that this is going to be equal to e to the x. And the x that they're talking about here is negative 2. So what does this converge to? Good. E to the negative 2nd power, or 1 over e squared. Very good. So x is equal to negative 2, and we're using rule 5. Okay, and then this last one has to be rule 6. It's got a factorial in it. X in this case is what? 100, that's right. And this is going to approach 0 by rule 6. Okay, so those are several examples where you can just use these rules and get the limit. All right, another type of sequence that I want to talk about is called, well, the Fibonacci sequence is an example of a certain kind of sequence called a recursive sequence. And that's what we're going to do in the next video. I hope you found this video helpful. If you did, please give it a thumbs up. That will help other students to find the video. You can also subscribe to my channel, Miss Hearn Mathematics, for more math videos.